Hello everyone, my name is Kevin Tarr. I am the iOS engineer and today is day 25 of Algorithms in Swift. So to celebrate day 25, we're actually going to be taking a break from coding and going into Greek philosophy and ancient algorithms. Okay, now we're not going to be taking a break from coding, but we actually are going to be talking about Greek philosophy today and ancient algorithms. Okay, we're going to be using a very, very ancient algorithm that's over 2 to 3,000 years old, um, called Sieves of Eratosthenes, hint, to help us solve our problems today. So if you're familiar with Greek philosophy, and if you had some exposure to the Sieves of Eratosthenes, then I think that you'll be able to find this problem quite charming and a bit of a break to solve. But if you haven't been exposed to it, this problem could be pretty complex. So let's begin. So our problem states write a function that returns an array of prime numbers from 2 up to but excluding a number, taking care to be as efficient as possible. Prime numbers up to 10 should return 2, 3, 5, and 7. Prime numbers up to 12 should return 2, 3, 5, 7, and 11. Prime numbers up to 100, I'm going to take a deep breath before I say this. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Whew! Okay. So let's take a bit of a history lesson with the Sieves of Eratosthenes, okay? So the Sieves of Eratosthenes is an ancient algorithm that dates back 2,200 years ago. Its core premise is to identify every single prime number up to a certain number. It is incredibly brilliant, incredibly simple, and incredibly efficient, which is why we still talk about it today in 2019. The premise of the algorithm, the way it works, is that we assume every single number up to a certain number is prime automatically until told otherwise. So we have a number chart here from numbers 1 to 100, and we can apply this algorithm right now. Okay, so we start with 2 because 2 is the number in our problem, and we assume that 2 is a prime number. So now that we've assumed that 2 is a prime number, we take all of its multiples from 2 to 100, 4, 6, 8, 10, 12, all of them, and mark them as not prime because they're multiples of 2, and they are not prime. And a prime number is not supposed to have any multiples attached to it. With that logic, we go to the next number, 3, and assume that 3 is a prime number. And we take all of its multiples. But before we take all of its multiples, to optimize our problem, because we already have the multiples of 2, we can go directly to squaring 3 to 9 rather than doing 3 times 2 because that's already taken care of. We have 6 already marked off. And we have every other multiple of 2 already marked off, okay? So we go straight to 9 and then proceed going forward. 12, 15, 18, 21, so on and so forth. Then we go to 4. 4 is already a multiple of 2, so we don't have to count for 4. So we can go directly to 5. 5, we can see all of its multiples, 5, 10, 15, 20, mark them all off as not being prime. 5 is prime, okay? 6 is marked off. 7 is prime. We square 7 directly to 49. We don't have to worry about any other numbers, any of the other numbers in between because they've already been marked off. And we go from there. 56, 63, 70, 77 we mark off. 91, and everything else is already marked off of 7, okay? So we go to 8, 9 is already marked off. 9 is already marked off. 10 is already marked off. And we have 11. Now, there's no need to go past 10 because 10 is actually the square root of 100. And if you watch the prime video that we did on prime numbers, we already came to the conclusion that any two numbers that are greater than the square root of a number multiplied together will be greater than the number itself. So we don't have to go past 10 in order to know all the prime numbers. We already have all the prime numbers. If we do 11 squared is going to be greater than 100. So every number here we have already found to either be prime or not prime. It is that simple, that efficient, and that brilliant. So brilliant and so simple and so efficient that it's taught to kids all across the world. Okay, so now the class is over. Let's apply the Sieves of Eratosthenes to our problem today, okay? We're going to call this problem prime numbers. pass in integer, return array of integers. We're going to check just for edge cases to check to see if our integer is greater than 1. If it is, we're going to continue our problem. If not, we're going to return an empty array. Okay. Then I'm going to create an array of Boolean values. Actually, this is going to be our way to confirm, to assume that every number is in fact a prime number, unless we find out that it's not. Okay. And we're just going to flip, we're just going to flip 0 and 1 to be false immediately, because we're counting up to 2, and we both know 0 doesn't count, 1 is not really a prime number, but it is kind of sort of. Okay. So now we're going to go through this function for number and 2. Oh, in fact, let's actually get square root. We want to actually reduce this problem and be accountable for time. So let's get square root. Okay, and we're going to count up to the square root, inclusive. Then we're going to ask if the number is in fact a prime number. If it is a prime number, then we're going to get all of its multiples and use a stride method, and we're going to square number up until it's, the actual parameter, the argument is passed in, excuse me, by the number. Okay, that's just striding it from the multiples until it gets to the number that's passed in. In this case, we try 100. Okay, and we're going to mark every multiple as being not a prime number. We're going to mark it as false. Okay, and then we're just going to return an enumerated array of C numbers. We're going to compact map it, and for every element that's true, we're going to ask if each element is true. If the element is true, we're going to return the number, and if not, we're going to return nil. But since we're compact mapping, we're going to flatten out the nil values and erase all the nil values, and we're only going to return all the numbers that actually are prime numbers. Okay, with this ternary operator and with the compact mapping. So let's actually run this function. Prime numbers. Let's do 100, and let's see if we can print this actually. Yep, 2, 3, 5, 7, 11. These numbers match exactly this test case right here. Let's do 12 really quickly. Okay, and let's do 10. Boom. Okay, so history was with us today. The Sieves of Eratosthenes actually helped us solve this problem. This is a really, really brilliant and simplistic solution in solving this problem. It's very efficient. It almost feels like cheating, but it is a very, very powerful and efficient problem, efficient solution to solving this problem. A very daunting problem at glance, but children have been taught to use this solution to solve this problem. So guys, let me know what you think in the comments below. Please share any proposed solutions you have to this problem. And if you have any comments about the Sieves of Eratosthenes, Greek philosophy, or anything regarding prime numbers, I'll be willing to discuss with you in the comments below. Thanks again.